All right, so in my last lecture, we talked about water and how it was polar. So now we're going to look at the consequences of water being polar. So like we discussed, oxygen has a partially negative charge while the hydrogens have a partially positive charge. And what happens is if you imagine water when we look at like a cup of water, it's not water by itself, it's not one atom, it's millions and billions and moles of water. So what happens is you'll have other water interacting with this water atom here. So if I have another water like this, understand this oxygen is also a partial negative. And what happens is these hydrogens that are partial positives, just like in ionic bonds, is somewhat attracted to this water. So there's going to be a weak attraction, right? And there's more and more water. So this partially negative oxygen is going to be attracted to another partially positive hydrogen. And if you imagine all these thousands and millions and billions of water, there's tons and tons of all these really, really weak interactions that kind of make a huge mess. But these interactions, because they're between a hydrogen and an oxygen, a hydrogen and any polar molecule on a separate atom, these are what we call hydrogen bonds or H bonds, right? So it could be between this hydrogen and let's say nitrogen, or hydrogen and like a fluoride. The important thing is that they're on different atoms. So for example, this hydrogen, this oxygen, this bond right here is not a hydrogen bond because they're on the same molecule. This is a traditional polar covalent bond. These two are hydrogen bonds. And the thing about hydrogen bonds is that they're very transient. They only last for a very short time. However, there are millions and billions of these bonds, and what happens is they keep water very close and tight and kind of sticks. It makes water kind of stick to itself. It's a very cohesive substance, and we'll talk about that a little bit later. But I want to get you familiar with these two terms, which is hydrophobic, and hydrophilic. Now they sound very familiar, so just think about philic and phobic. Phobic, Greek, like phobia, to be fear, to be afraid of water. And things that are afraid of water are basically things that are non-polar, right? Like oils. If you ever think about oil inside of water, oil doesn't interact with water because the oil molecules, which are mostly carbon and hydrogens, are very non-polar. Whereas oxygen has all these kind of hydrogen bonds and all this polar stuff going on. It's not going to really interact that well, which is why water, if you mix water with oil, oil kind of rises to the top. It doesn't want to deal with water. It's scared of water. On the other hand, we have philic, like philanthropic, which means to love. And things that love water are things that are polar. So if I look at, say, sodium, right? Sodium chloride, salt that we talked about before. If I dissolve this in water, what's going to happen is, well, the fact that it dissolves in water shows that water will readily interact with it. Because water has all these oxygens that are partially negative, right? And I put a positive sodium ion here. This sodium ion is real comfortable because it's like, hey, negative things. I like negative things. Oh, we're comfortable. I'm gonna try to chill and kind of interact with these guys. I'm happy. This chloride right here, it's saying, hey, I see lots of positive, partially positive hydrogens chilling around, right? I'm 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 finna interact with these guys. Ooh, I'm comfy, right? So not polar things love their fill it. They love this water. Oils, non-polar things, they're like, ooh, ugh, water, nah, not about it, right? So understand, just think phobia, philanthropy, right? Love, hate. That comes into very important when we talk about membranes later because things are either hydrophobic or hydrophilic. So back to the part about water sticking to itself. There are kind of the three main consequences of that are adhesion, cohesion, and surface tension. So let's start with adhesion. Adhesion, basically, think different. Water adhering to things different than itself. So if I look at, say if you put water in a test tube, this is the example they give in the book. If you look closely, the water kind of does this kind of thing, right? Because this is called meniscus, by the way, and it forms because water would rather, in this form, it kind of sticks up higher against the side of the test tube, which means it has more adhesion, it has more ability to stick on other things. If you think about like right when you get out of the shower, water kind of chill on your skin. It doesn't kind of roll off; it kind of stays there. It's sticking to your skin. That's also adhesion at play. Cohesion is water sticking to itself. Itself. I can't even spell. If I put a droplet of water on, say, any surface, it's going to kind of make this kind of shape. It's not going to spread out easily. It wants to stick together. That's cohesion. Water really wants to stick to itself. And finally, if I look at surface tension, think about jumping into a swimming pool like doing a belly flop on a swimming pool. It hurts. Why? Because water doesn't want to break up. It wants to stick together, especially at its surface. So if I look at it like a surface of water, this water on top right here, really strong tension. It really wants to be together right here. So and all three of these are consequences of its hydrogen bonding and its polarity. Water really wants to stick to other things, which is its cohesion, but it wants to stick to itself, and that's it wants to stick to other things, which is adhesion. It adheres to other things, but it also sticks to itself and makes really tight surfaces, and that's the cohesion and surface tension. All these are consequences of its polarity. So understand that these three things are very important properties of water. Another important thing about water is density. Typically, when we look at things, if I draw a graph, this is your density, and this is your temperature. As your temperature gets higher and higher and higher, things get less and less dense, right? Like air. Hot air, high temperature, is less dense than cold air, right? But water, this is a really cool thing where like other things, as your temperature goes down, it's getting more and more dense, Except when you reach about kind of 0 degrees, it kind of does this thing, whoosh, where the coldest water is actually not as dense as the warmer water. And this is around freezing point, 0 degrees or 32 degrees Fahrenheit. And that's because when water freezes, it forms this lattice, right? This solid structure where all the hydrogens and all the oxygens are bonded via these really, really strong, solid H bonds. All right, and these H bonds are really, really far apart, which makes up this really, really, you can imagine like tons and tons of this thing that makes up this giant lattice. And this lattice is what forces water to take up much, much more space, right, which makes it less dense. The same amount of water, but if you spread it out into a bigger area, bigger volume, it becomes less dense. And when things that are less dense tend to float, which is why ice floats on water. This is a really weird phenomenon that you don't see in most other substances. You don't ever see that. And it's really important because if you think about life, if water froze and sunk, right, then the bottom of all your ponds and lakes would kind of freeze over at winter, and that kills all the life down below. However, in our world, because water floats, because the ice floats, it allows the water underneath the ice to be nice and warm and nice and fluid, which allows life to continue. Another important property of water is its high specific heat. So the way you think about this is, imagine we have a really sunny day, all right, and this is sun, and you put a cup of water underneath the sun, and you put a piece of, let's say, metal, right? Leave it there for an hour. You touch the water, it's still kind of cool, right? Think about like a swimming pool. If you put a swimming pool all day in the sun, it's still relatively cool. However, the metal, if you just leave it on the sun for like a few minutes, it's gonna get hot, right? And this is the high specific heat of water. All it means is it takes a lot of energy to warm up water. And the reverse is true, which means it only takes a little bit of temperature change to make a lot of energy released from water. And that's important if you look at like shoreline temperatures, right? So if you look at maps and you compare temperatures inland and near shores, you realize that things inland, like a desert, have a much greater change of temperature than things at shore. Shore is kind of really kept in this really close range. And that's because you have all this water around, because water has a really high specific heat. So in the desert, in the sun, like think about metal, right? In the sun, it's going to get super duper hot. Nothing else to absorb the heat. And at night, there's nothing else to hold the heat. So it's going to get super, super cold, like metal at night, right? However, in the shore, when it gets hot, this water is going to absorb a lot of the extra heat, right? So it's going to keep it nice and cool in the day. But at night, whereas this metal gets super duper cold, the deserts get super duper cold, we have this water that's holding a lot of energy. It's not changing that much of temperature, but it holds a lot of energy. So it's going to give up a little bit of temperature, just a little bit of temperature, but it's kind of that all that energy going to keep the air nice and warm. So that's why you have a much milder temperature near the shores than you do out in the deserts. And that's also based on water. So back to what I was saying, the water's high specific heat is due to these strong bonds it makes. It's really strong polar bonds that it makes intramolecularly, those H bonds, which basically allow it to have such strong, high specific heat. And finally, we're going to talk about a little bit about acids and bases. So again, this is a review of chemistry. If you took chemistry, like you know, we define something's acidity based on its pH, which is the log of the concentration of hydrogen, right? So if I have a really high, the negative log. So if I have a really high H concentration, so if I have a high H concentration, something's really acidic, the log is going to be positive, really high too. But because we're talking about negatives, it's going to get smaller, right? So acid high means your hydrogen concentration is high, which means your pH, because it's negative, is actually low, right? Same thing if something's very basic, right? So lots of basic, that means your hydrogen concentration is low, which means the negative log of that, the pH, is going to be high. So think low pH, think acid, high pH, think base. And then we talk about a little bit about buffers. So what buffers do is they kind of like what the water does here, is they kind of keep the range small, right? So we have buffers all in our body systems, like in our blood, in our interstitial fluid. You'll learn this much later. But instead of like the desert or the metal, where a small change in temperature is gonna change a lot in the heat. Here in the acids, instead of having a small, like if I add a little bit of acid, it's not gonna make that big of a difference because we have all these buffers. So when you think about buffers, think about homeostasis, think about keeping it in a set point, right? You don't want things going all over the place. Instead of going from here to here, buffer's gonna say, hey, let's just keep it from here to here. No big changes. We're gonna keep it right in this sweet spot. Anyways, so this is my overview of water. In my next lecture, we're going to talk about chemical reactions, heat of energy, Gibbs free energy, and then finally we're going to look at carbon, and that's it for the first part of biology. All right, thank you.